Hey everyone, this is Mrs. Johnson. This is MAT 221, Calculus 1. We're looking at section 2.4, talking about continuity from our Stewart text. So let's talk about a definition of what does it mean for a function to be continuous. Most techniques of calculus require that functions be continuous, and a function is continuous if you can draw it in one motion without picking up your pencil from the paper. Now that is an intuitive definition, it's not a mathematical definition. And our textbook, the Stewart text, uses this definition for continuity. Just so you guys are aware, there are many other different books that use a different definition of continuity. Our book is using this definition that if you can draw the function in one motion without picking up your pencil, then it would be continuous. A function is continuous at a point if the limit is the same as the value of the function. So let's look at this function that we have here. I have a piecewise function that we've actually looked at in a previous section. If we look at this function, we would say it's a piecewise function. It's defined by a linear and then a constant function. Then it has a dot, has a linear and another linear, all pieced together in one domain from 0 to 4. We can definitely see that there's discontinuity at x equals 1 and x equals 2. And we're going to talk about the different types of discontinuity in just a second. But if I were to draw this and stay on the function and draw the function with my pencil, notice I would have to lift my pencil at x equals 1 and lift my pencil at x equals 2 in order to draw the function. These are considered points of discontinuity. Now notice the discontinuity at x equals 1, there's a gap in the range. The discontinuity at x equals 2, there's only just a little a point that just gets moved off the function. So let's talk about what types of these discontinuities are. By the way, before I move on, this function is considered continuous at the endpoints. Notice at x equals 1 and at x equals 4, there's solid endpoints there because the value of the limit, the one-sided limit, in the first case at x equals 0, that means that the right-handed limit exists and equals 1. And over here at x equals 4, the left-handed limit exists and happens to also equal 1. And because the value of the function equals the value of the limit, then we say that the function is continuous there. Notice at x equals 2, the value of the function is actually equal to 2, but the value of the limit does exist and equals 1. At x equals 1, notice the value of the limit doesn't even exist because I have two different targets as I come and approach 1 from both sides. So let's go through these types of discontinuities. The first are called removable discontinuities, and removable discontinuities look like this. They look kind of like bullet holes in the function. And we saw one example in that last example, we saw that bullet hole in the function. So if you have a point of discontinuity where there's a hole in the function, for instance, in a rational function where I cancel out the linear term in the numerator with a linear term in the denominator, that would cause a bullet hole in the function. Or if I had something like this, which is a piecewise function, which has a limit, but this hole or this dot is not in the proper hole in the function. So anytime you see a hole in a function like this is called a removable discontinuity. And the reason why is we could remove the discontinuity by simply bringing the point down to the hole, or in this case, defining the function in a piecewise way where you could actually fill that hole. The other types of functions, the other types of discontinuities that we study in calculus are called essential discontinuities, and we really just need to know two of these three. The first one is called jump discontinuity. And jump discontinuity is when there is a huge gap in the range, but there's not just a hole in the function like this. Notice this is just a hole in the function. Here there's a real big gap in the range of the function, where the range is down here, and then there's a jump in the range, and then the range continues. That's considered jump discontinuity. The second type of essential discontinuity occurs when we have vertical asymptotes on a function or in a function, where the discontinuity is infinite. In other words, in this particular case, where I have the function y equals x to the negative 2 or 1 over x squared, I have a vertical asymptote at x equals 0, and I have what's called infinite discontinuity. I cannot fix that discontinuity. That's called infinite discontinuity. This next type is called oscillating discontinuity, which we actually don't have to study in Calc 1. We'll talk more about oscillating discontinuity when we get to Calc 2. So, some more on continuity and discontinuity. Let's look at a more mathematical definition. This is the definition mathematically. A function f is continuous at x equals c if it is defined at that value, in other words, if it has an actual value there, and the value of the limit as x approaches c is equal to the value of the function at x equals c. In other words, f of x is as close as we want to the value of the function, provided x is close enough to c. And we also will note that a function can be continuous on an interval from a to b if it is continuous at every point in that interval. Sometimes we have non-continuous functions that are continuous in some intervals along that function, but not throughout the entire domain. In other words, here's our definition of continuity for us. The continuity formula or definition here actually says 3 things. So we have to have 3 things in place in order for a function to be continuous at a value at x equals c. First, the value of the function has to be defined. In other words, the function somehow has to have a solid dot somewhere at that value at x equals c. Secondly, the value of the limit must exist, which means, just as we said in the last couple of sections, I have to have a targeting value. As x approaches c, the output of the function has to target the same y value from both sides. And lastly, the value of that function and the value of the limit have to equal each other. Otherwise, we say we have discontinuity at x equals c. So let me give you an example. Here is a figure of a function f of x. Where do we have discontinuity and why? And I'm going to go a little bit further and ask you, what is the discontinuity at each one of these points? So if I look at this function, going through our definition, where do I have to lift up my pencil from the page? Well, right here I have a hole, so I would have to lift the pencil from the page to go around that hole. So I have discontinuity at x equals 1. I would also have to lift my pencil from the paper to get here and then continue to draw. I would have to lift my pencil again at x equals 5 to get my function. So I have 3 points of discontinuity at x equals 1, at x equals 3, and at x equals 5. Let's go through the process of those 3 procedures here. Now remember, this was our 3 procedures. The value of the function has to be defined, the value of the limit must exist, and the value of the limit must equal the value of the function. So let's look at each one of these scenarios. At x equals 1, let's go through our 3 things. Does the value of the function exist? And the answer is no. I have a hole in the function and no solid dot at all anywhere at x equals 1. F of 1 does not exist. Therefore, in my formula, part number 1 is not met. Therefore, my function must be discontinuous. In order to be continuous, all 3 of these must occur. So at x equals 1, I have no value of the function. The function is not defined at x equals 1, therefore discontinuity. What type of discontinuity do we have here? We have removable discontinuity because there's like a bullet hole in the function and there's no dot anywhere else, no jump in my in my range. Now let's look at x equals 3. At x equals 3, let's go through our definition. Is the value of the function defined? Yes, the value of the function at x equals 3 is this solid dot right down here. Now I don't know what the actual output value is, but it's right here at x equals 3. Secondly, does the value of the limit exist? Well, let's look. My targeting value from the left targets this value of output value of y. My targeting value from this side targets this value of y. Those are two different targets. So the value of the limit does not exist. So part 2 of my definition fails. Therefore, I have discontinuity. What type of discontinuity? Notice there's a big gap in the range here. Not just a dot, but a huge gap in the range. Therefore, I call this jump discontinuity. At x equals 5 is my last possible point of discontinuity. Let's go through my 3 parts of the definition. Is the value defined? Does the limit exist? And does the value of the limit equal the value of the function? So let's see. Do I have a value of the function at x equals 5? Do I have f of 5? Yes. I have a solid dot up here. The value of the function at x equals 5 is that solid dot. Secondly, do I have a value of the limit? Remember, the limit says, do I have a targeting value from the left and a targeting value from the right? Yes, I do. Do they agree? Yes, they do. They're targeting that open circle there. So the value of the limit does exist and equals whatever that output value happens to be. But in this case, step 3 does not work. So we have check, the value of the limit, the value of the function is defined. The value of the limit exists. But part 3 of this definition is failing. The value of the function and the value of the limit do not equal each other. Therefore, I have discontinuity. And again, this is called removable discontinuity, where I have a bullet hole in the function. Even if I have a point up here that looks like it's jumping up there, I don't have a huge gap in my range, because as soon as I go to that point, I go right back to that same range value. So this is called removable discontinuity. So there's our 3 scenarios. Notice those 3 things have to be in place in order for a function to be continuous. Here, the value of the limit, the value of the function did not exist. Here, the value of the limit did not exist. And here, the value of the function did not equal the value of the limit. Therefore, all 3 places have points of discontinuity. Now, what about if I didn't have a graph, but I had functions? So let's do a little bit of analysis here. Although we could do a lot of these on Mathematica, we could put them in and look at the graph. Let's see if we can do a little bit of the analysis before we move forward. In part A, if I look at this, this is a rational function. I have a polynomial over a polynomial. In this case, a quadratic over a linear. Now remember, I would have discontinuity at x equals -2. Possibly there's 2 things that could happen. I could either have a vertical asymptote or I could have a hole in the function. Now if I factor this numerator and factored it out and then looked at the function, this would factor a factor of x. So if I were to factor that numerator, I would factor it x minus 2, x plus 1. And I know that I would cancel that factor. And what happens with a rational factor rational function when that happens? What happens is I have a hole in the function. So do I have discontinuity at x equals 2? Absolutely. What type of discontinuity do I have? I have removable discontinuity. Now, what about at b? This is a piecewise function. This looks like the function, the power function x to the -2, right, which looks like the curtain function. So if I were to graph this function, it would look something like this. So it looks like those curtain functions, but it says everywhere else except for at x equals 0, and then at x equals 0, I just have a dot. Okay. Does that remove my discontinuity? No, I still have infinite discontinuity at x equals 0. I still have a vertical asymptote. Even though I just dotted that point there and the value of the function is at 0 is equal to 1, it still doesn't remove my discontinuity. So I still have removable discontinuity at x equals 0. Now, if